Right. What I will do is first let's discuss the need for MPPT, maximum power point tracking. Right. Maximum power point tracking is well, sometimes not necessary for small projects, but as you can see, if I calculate here why maximum power point is needed, the behavior of a solar module is that it gives you power at a rated current and rated voltage. We look at the 12-volt module, the so-called 12-volt module. The solar module will give you constant current for a range of voltage that is from 0 to the maximum voltage of the module. But the voltage does actually can drop on a constant voltage. So a 12-volt module will give you, on average, if I show you the collected data of the modules, as you can see here, for a 36 cell, which is number of cells here 36, you can see that the maximum voltage VMP is around 18 volts, and for a given wattage, well, the current is also given there. The power rated divided by 18 will give you the current that the module will give you, and this current normally stays constant for a range of voltage. So what we do is we look at the constant voltage. The constant voltage for the maximum power, 100 watt solar module divided by 18 volts, that will give you 5.5 amps. Right, you connect this module to a battery, a 12-volt battery. A 12-volt battery, we know a 12-volt battery gets up to 14.5, 14.9, depending on the manufacturer recommendation. Right, we are going to use 5.5 amps charging that battery. Right, suppose the battery is at 12 volt, so we say it's 12 volt times 5.5. So the module will actually give you 66 watts. That is when connected straight to the battery. The maximum power that you can get from the module is 66 watts. Suppose you have a gadget that actually would maintain the solar module at 18 volts. It means if module is connected to a battery of 12 volt and it's giving you 18 volts, it means you are actually saying it's 18 volts times 5.5, that is got 99, almost 100%. Well, we're looking at plus minus there. So well, normally the battery will not stay at 12 volts. Suppose you are actually charging that battery and it gets up to 14 volts, and it's 14 volts at 5.5, that's 14 volts times 5.5, that's 77 watts. That's the maximum the module would give you. Why it does, we are calculating this, we are saying, okay, whereas you connect the module to the battery, the module voltage equals the battery voltage because they are just connected straight. But if you have a gadget that actually would regulate the voltage or voltage change, you would have the maximum power of the module. But if you connect straight, it actually goes down. That's how the power, what we call the power switch modulated charge controllers do. They are just switches. They switch the solar module straight to the battery, and when the battery fills up to the set voltage, it switches off. So you are like you are connecting the module straight on the battery, and when the voltage of the battery gets to a point where you need it to be, you remove the connection like that. That's how the other solar charge controllers will do. But the MPPT charge controller does, what it does is it converts the voltage for the solar module down to 12 volts. So you can see that at 77 watts for a 100-watt solar module, you're actually having 77%, we'll say 80% of the 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 power that you can get, which means you are actually saying it's 4 divided by 5, that's about 80%. Okay, so when you do not have a maximum power point trigger, you are actually like saying you buy 5 modules and you use only 4. The fifth one, you actually do not use it. So that's the loss that you have. It's around 20% loss. So that's why big systems, they are very much concerned about the maximum power point tracking. This is the reason why. So that's the need for maximum power point. But for small systems, the loss, the 20% loss, normally you don't feel it, because you don't even see it, and you don't even recognize that you are losing, because usually you overbuy, you buy a bigger solar panel for your needs, and the losses, well, it's just going down the drain. But for big systems, it matters, because it becomes an amount of money that you should be worried about. The other need for a solar charge controller that uses power supply, a DC to DC voltage regulator, or a power supply that has got a transformer isolation, the various types of DC to DC converters, is that you can actually connect a higher voltage solar module here, charging a smaller voltage battery system here. Like these days you have the 72 cell solar modules with output voltage of now 50 volts. They are now cheaper than smaller modules, which are 50 watts, 100 watts. So you can have a 350, 360, 400 watt solar module charging a 12 volt battery. That is now possible with the solar charge controller, which has got a power supply. The maximum power point tracking feature is mostly an added feature to charge controllers, and it's only for the purpose of efficient harvesting of energy. That's an advantage. I've seen installations where people connect a 330, 350 or 400 watt solar module and charging a 12 volt battery. It appears like it's working for a few months, but later on you have problem of the charge controller and even the battery getting damaged, because the system is not balanced. The best charge controller to use there is an Mppt charge controller. The efficiency of solar panels is around 20% now, but well, the research as of today, I've read there is now getting to around 50%. They are now close to 50%, which is good. So solar technology is improving, but very soon maybe we'll get solar modules that are above 20% efficient. And well, nowadays you have modules that are 500, 600 watt without much change on the size of the module. I've done the solar charge controller using Mppt fixed voltage, and I've seen some improvement on my system. There is great much improvement, very much big. Like you actually see it. You see the change. You see that you can much use power in the afternoon much more than you were not. So yeah, it does have an effect. I do not actually upload videos of things that I have not done, that are theoretical. I upload videos of the things that I have actually made and tested. I'm using this solar charge controller, and it's wired to 2 times 150 watt solar modules. They are old. They are the standard size 155 millimeter by 155 millimeter from, and these are the diodes, the Schottky diode. These are the Mosfets. They are actually the high side Mosfets. This is the inductor that I've used, the choke. This is from a welding machine, the Thermadyne, if I'm not mistaken. It is a Thermadyne welding machine. The input capacitor, and here is the power supply for driving the Mosfets, the high side power supply here to drive these Mosfets. And then here is the sleep circuits. Here is the Mppt circuit. There is a 555 timer there under. Right, let me try to get to another. Yeah, Schottky diode. That's a 30 amp. Well, you can see here. I think that's 30 amp, 40 volts. I think, according to that. Right, Mppt circuit is here. The choke or the inductor is here. Mosfets there. Right, and then I can just say closer. Power supply transformer here. That's the transformer. The transistors for the relaxation oscillator. That's one of them. The capacitor there. And then what else? Same. Right. The sleep circuit, a relay there. The fan is here. The fan control circuit is there. The thermistor is actually attached to the inductor there, under there, and the wires, these green wires, are coming from the thermistor, and then that's the comparator, and then the D-latch, that one. Right, and then sorry, can go back. Here are the back current Mosfets. They are here. This is the negative. Well, it's red. Sorry, I just use the wires that I have. Normally, when I build these things, I'm building like I want to see if this thing is working, and I build it. I'm thinking about it. I just pick a wire and use it. It's red, but this is the negative, but negative. Or the common negative, and this is the solar negative. They are switched here using Mosfets. Okay, the fan there, and in the enclosure, this used to be an inverter enclosure, TES inverter, South African made inverter. Right, then I took out the transformer and the circuit for the inverter, used them somewhere on my inverters that I built, and then the circuit for the solar charge controller, I put it in there. Right, yeah, this is almost like the whole circuit together. This is the TO494 I see here. This board is driving these Mosfets here, driving these Mosfets. Okay, right, and then the fan control transistor is that one. The IC. This is the LM393, the D-latch here, 4013 IC, and the Mosfets for the back current switch here. And then the fan, of course, that one is the fan, of course, and right, the fan. As you can see, it's actually picked from a disused equipment. I think these fans were coming from computer power supply. This is a computer power supply fan. Still with its dust and all that. Yeah, they use recycled material. But this thing actually powers. You can actually power a television using this charge controller. Right, because it's basically a power supply anyway. Right, and then what else? I think there is no more. Okay, I think yeah, it's done. Okay, right. So this is my solar charge controller, and I think I will share necessary information on this one. I will give you the circuit diagrams of the charge controller. I mean this diagram here. I'll share with you. Here there is no program that I need to share with you because there is no programming that I have done. You can make improvements here like I was suggesting here. Let me zoom and talk about it here. Right, on the driver, you can use any driver that you wish. Usually the TOP 250 will do, but you can also use the IR2110 series or the HIP 4081, which is now obsolete. Well, it's not anymore, or any other driver, but you should use a driver that drives the MOSFET properly. My next video will be the 48 volt inverter that I have actually built, and it's gonna be a bit long because, well, I think it's a big circuit that I have to describe. Thank you.